Hey guys, welcome to another lecture in the Math 4000. So this will be lecture 13.1. So I will continue with more continuity. In fact, I would like to continue more with talking about continuity on compact intervals. Also, I'd like to talk a bit about density as well. So let's get started. Now, I would like to start with something. Well, remember we did this problem last time. And the problem that we did was the following. Remember, it was this one here. I want you to look at it. Right, this was this problem number 3 here, which essentially says that, well, I'll state it as a theorem now, because last time, if you remember, I gave you these 3 theorems. Look at them. So we said that if a function has the intermediate value property and moreover is one-to-one or injective, then this will imply continuity. Then also, as you can see, continuity and one-to-one will imply strictly monotone, and also, combining the first and the second one, the intermediate value property plus injectivity will imply strictly monotone, right? Because continuity plus injectivity will imply a monotonicity. All right. But also in this problem 3, there is one thing that we did and we actually proved is that if you look at part B where we said this is true, right? We'll look at this here. If we say that f is monotonic, whatever, or monotone, you can say, and the range of f is R, then f is continuous. So in other words, well, we can say the following. So we can say that we have the following, theorem. Let's call this theorem 4. And we can write it like this. Let's say strictly monotone, or although I shouldn't mention this, when I say monotone, I mean strictly monotone, plus surjective, or I can say here onto implies continuity. So that's the thing that we need to remember from this one. All right. Now, combining these theorems, I would like to talk about a problem. So let's talk about problem 4, which is pretty standard, but anyway, it's good to know, because in this way you can operate with these theorems, but also with the functional equations involving continuous functions. And the problem says the following, pretty straightforward. It says that show that there is no function, say f defined on R and real valued, continuous, such that f of x is negative x. So that is the statement of the problem. All right. So as you can see, we have a functional equation. As you can see, we have the composition of 2 functions here. We have the composition of f with itself, and it says it's the negative identity. So assume by contradiction that there exists f continuous such that f composed with f of x is negative x. Okay. All right, so we know that f is continuous, but now we can prove something. Maybe we can prove that f is injective. So now, next we show that f is 1-to-1. Or we can say it's injective. All right, so now let's consider x1 and x2 such that, so let x1 and x2 real numbers, such that f of x1 is the same as f of x2. All right, now by composition, this implies that f of x1 is the same as f of x2, or which is equivalent, but we know from the functional equation that f of x is negative x, so this will imply negative x is the same as negative x1 is the same as negative x2, which clearly implies that x1 is equals x2. So f is 1-to-1. Or injective. Anyway, sometimes I'll refer this as 1-to-1. Sometimes I'll use the word injective. It doesn't really matter that much. All right, but now by a theorem, what theorem was it? Let's look. As you can see here, by theorem, well, it's not quite here. Continuity by theorem 2, right? So by theorem 2, it follows that f is monotone. When I say monotone, I mean strictly monotone. Okay, f is monotone, but we know that the composition of f with itself will always be increasing, but f composed with f of x is an increasing function. While the function, let's say, the function, let's say g of x equals negative x is decreasing. So that's a contradiction. Right, we cannot have a function, a strictly increasing function to be equal to a decreasing function. That's not going to happen. Where did the contradiction come from? Well, by our assumption that the function, there exists such a function. Therefore, there is no such function. Such function f. And that's it. So this is how we solve this kind of problems. You'll see that in the recitation, I'll do something similar. There will be a, I think, some Romanian Olympiad problem, but it's related to another Putnam problem. Anyway, you'll see in the recitation. All right, now I want to veer towards something else. Like I mentioned at the beginning of this lecture, is I would like to talk about something about continuity, because there is an important theorem here on closed and bounded sets. In fact, when I mean sets, I mean intervals. And there's this theorem, very important theorem that you learn in Advanced Calc 1, right? In any introductory course in analysis, which is due to Weierstrass, Karl Weierstrass, which says the following: if I have a function defined on a closed and bounded interval, AB, real interval. Well, it's in R, and in fact, even in Rn, we will say that closed and bounded is the same as compact. So we have, if this is continuous, then F is bounded. On the interval AB. But moreover, it doesn't happen just that. Something else is something even more important is happening here. F attains its bounds. Which means that there exists, let's say, an xm in an AB such that f of xm is the, let's say, the infimum over all x in AB of f of x, and also there exists, let's say, an xm again in AB such that f of xm will be the supremum of f of x. Okay, so this is very important. So this is the more important part. And now I would like to point out a remark. Anyway, this is a little bit of a crash course in advanced calculus. That's not my intention. I'm just gonna stick to the essential part of it. I'm not gonna go too much into theory at this point. But now I would like to definitely I would like to point out something here in this case, and if the interval must be bounded because it's very important. So if the interval is not bounded, then the theorem is not valid anymore. So like I said, this is an essential condition, and the example given, so the counter example is given by let's say, let's consider this function. F of x is 1 over x, and let's just say f is defined on an open interval 0, 1 and real value. This is continuous, so which is continuous but not bounded. But not bounded. All right, and I believe you can cook up many other functions as well. All right, so this is one thing. Also, I'd like to point out, so from here, another theorem which is important, which will tell us how we can transform intervals through continuity. And basically, this theorem says the following: if I have a function defined on a closed and bounded interval AB, with real valued, if f is a continuous function, then it is very important here, then f of this closed and bounded interval AB is a closed, I think it's important here, closed and bounded, and therefore we can say the compact interval. This is very important to know. So look at, all right. Now, Now, I would like to mention one other thing. Like I said, this very short. It's a crash course in analysis, in real analysis. I would like to say a few words about uniform continuity. And I'd like to start with the following definition, which says the following. So a function, let's just say f defined on a domain D and real valued, is uniformly continuous this guy is uniformly continuous on D if for every, let me write it like this, if for every epsilon positive, right, there exists a delta positive such that for all x and y, for all x, y in the domain D with x minus y in absolute value less than delta, we have that the absolute value of f of x minus f of y is less than epsilon. Well, as you can clearly see from this definition, this will imply that, so let me point out a remark. Clearly, this will imply that uniform continuity implies continuity, but not the other way around. But there is this theorem which tells us exactly when a continuous function is uniformly continuous. And the theorem says the following: if f is defined on a closed and bounded interval a, b, is continuous, then f is uniformly continuous. That's what you need to know, right? Okay. Now, in what will follow, I'd like to stick only to problems, and now I'd like to talk about problem 5. And the problem 5, which is a must, is what we call the Cauchy functional equation. And I believe we have done this a long time ago in on the algebra, in elementary algebra lecture. I think it was lecture 2 or 2.1. I don't recall exactly, but I think we did this. But we did this. We found f all the way to q. So the Cauchy function equation says the following. We did not assume continuity though. So find all f defined on the on R and real value, all continuous functions such that f of x plus y is the same as f of x plus f of y for all x, y, and r. Okay, let's look at this. And remember what we did? We determined the function on the set of rationals, right? And now we would like to continue the procedure. So we in a previous lecture, I don't recall exactly which one, so I don't want to, but probably it was week 2. We showed that f of x is a times x for all x in Q, with a is f of 1. But now the question is, how do we pass from Q to R? That is a big question, right? But we have something which is important. So now we're going to use something which is called density, but we know that Q is dense in R. So we can find a sequence, let's say, of rationals. So we can find a sequence of rationals, let's say an, that converges to a number x, which converges to a real number x, right? So we can do this by the density, because of the density. And now let's look. So we have that, let's be careful now, f of an, we know that this is a times an, right? And now we would like to take the limit as n approaches infinity. So this guy, in fact, let me write it in this way. So let me put here the limit as n approaches infinity of f of an is the limit as n approaches infinity. Since we know that f of x looks like this, look here. Since we know that this is a times x for any rational x. So this would be the limit as n approaches infinity of a times an, right? But an converges to x, so this would be nothing else a times x for all x real. But okay, since now but on the other hand, f is continuous, so the limit, so this would be nothing else than just so this guy here is nothing else than just f of the limit as n approaches infinity of an, which is equal to f of x. Well, there you go. So the big part here was this guy here, that Q is dense on R. So we can find a sequence of rationals which converges to a real number. And this is how, so this implies that, so f of x is a times x for all real x, with a is f of 1. Keep that in mind. So this is how we solve the Cauchy functional equation. All right. Since we have this in mind, you have to know this. So you have to put all the pieces of the puzzle together now. If you can go back to the lecture. Unfortunately, I don't remember exactly which lecture, but I'm sure you'll find it. So once you put these pieces of the puzzle together, you can say that all continuous functions, real valued continuous functions, which are additive, because this is the condition of f of x plus y equals f of x plus f of y, it's called additivity, are these functions right here. So these are the functions that satisfy this. We have to keep this in mind. All right. Now, let me go further, sorry, with another problem, problem 6, which was a Putnam A2, well, a long time ago in 1947. So, whoa, long time ago. And the problem states the following. So find the functions f defined on R and real valued, which continuous, such that okay, in fact, let me write it like this. So find f continuous which satisfies for all real x and y, the functional equation. And the functional equation will be given by the following. So it will look like this. So f of the square root of x squared plus y squared is f of x times f of y. In fact, let me write it like this. Let f be continuous, which satisfies this, right? Prove that f of x is nothing else than just f of 1, everything to the power x squared. Okay. Look at the, well, I should have said a real valued continuous function satisfies this function equation. But anyway, I'm sure you understand, because the statement of the problem doesn't quite make sense, but I'm sure you understand what the problem asks us. All right. Well, this looks like a Cauchy functional equation, right? But we have to be careful here a bit. We have to, maybe in a certain way, we can reduce this to Cauchy functional equation. But not, but maybe for another function, maybe we should be careful here with, maybe we should consider another function. For example, so consider g of x to be, and let me take log, so the natural log of f of the square root of x. And g is defined on a set of non-negative reals and real value. Let's see, does this satisfy the Cauchy functional equation? Well, if you look at it, so this is the question, does G satisfy the Cauchy functional equation? So we need to, in other words, does G, is it true that G of x plus y is the same as G of x plus G of y? For all x, y, non-negative. That's what we need to show. So let's see who is G of x plus y. So we put some question mark here. So now G of x plus y is nothing else than just log of f of the square root of x plus y right? And this guy here and g of x, in fact, let me write it here, and g of x plus g of y, this is nothing else than just log of f of the square root of x plus log of f of square root of y, and this would give us a log of the product, so f of square root of x times f of square root of y, right? But we know, look at the, if we look at this guy here, if we take, but we know that f of square root of 5, so, but f of the square root of x plus y is the same as f of square root of x times f of square root of y. So G satisfies Cauchy's functional equation. Okay, that's great. But now, so we know how G would look like, but this implies that G of x is nothing else than just a times x. So this means that log of the of f of the square root of x is nothing else than just a times x, with a being f of 1 for all x are non-negative. And at this point, it's quite clear what will happen. This will imply that, so clearly, this implies that, yes, if we, that log of f of x, if you want, is ax squared, right? So f of x will be nothing else than just f of 1, so it's a to the power x squared. Let me write it like this. Yeah, where a is f of 1. And that's exactly what we're done. You see, a Cauchy functional equation comes into rescue at this point. So it was important in the economy of this problem. All right. Now let's see problem 7. So problem 7, again, it's a Putnam problem. It's a Putnam A5 in 1954. And the problem says the following. Again, this is a very, it's a classic problem at this point. So if f of x is a real valued function defined for all values of x between 0 and 1, then the formula, so we'll define what it means to, so then the formula, f of x is little o of x, probably you have seen this in computer science, is an abbreviation right? For the statement that f of x over x approaches 0 as x approaches 0. Okay, that's the definition of f of x is little o of x. Keeping this in mind, prove the following. If the limit of f of x is 0, and let's say that f of x minus f of x over 2 is little o of x, then f of x is actually little o of x. Okay, so that's the problem. I want you to look at it. Well, I would say it's a pretty straightforward problem. Tells you exactly what to do. So let's see. So now we know that the limit of f of x is 0. So what does this mean? But also we know that f of x minus f of x over 2 is a little o of x. So we should explore these two conditions here. This guy and this guy. There is no other option for us. And once we do this, let's see. So now let's consider, let me take an epsilon positive, be given. And now we're going to choose a positive delta such that for all x satisfying for all positive x which are less than delta, we have that 1 over x, right, times f of x minus f of 2x, right, is less than 1/2 times epsilon. Okay, so we know this. So, okay. Okay. All right, now let's see. Now let's fix y, and this y will be less than delta and positive, right? And then we can write this f of y as, and I'm going to write it in the following way so that you can see f of y minus f of y over 2. Now I'm going to reiterate, so f of y over 2 minus f of y over 4, right? Plus, and we keep going till the last one, which is f of y over 2 to the power n minus 1 minus f of y over 2 to the n, and plus the last one, so I'm just going to add and subtract this, guys, f of y over 2 to the n. So if we take the absolute value here, this will be less or equal, and we apply the, so this will be less or equal than the sum of these guys, f of y over 2 to the, f of y over 2 to the I minus 1 minus f of y over 2 to the power I, plus the last one, which is the absolute value of f of y over 2 to the n. And this will be less or equal than the sum of, so we know that this is less than, so the difference between any, this is less than 1 over 2 epsilon. So this would be y over over 2 to the power I minus 2 to the power I times epsilon, plus the last one, which is the absolute value of f of y over 2 to the n. All right, and now let's do some computations here. We have a geometric series where we can handle, which is, okay, so this would give us y times epsilon times, this would be 1 minus 1 over 2 to the n, plus the absolute value of f of y over 2 to the n. Okay, beautiful. And now clearly we're going to take n to infinity. So as n approaches infinity, we have that the absolute value of f of y is less or equal than epsilon times y. And since f of x converges to 0 as x approaches 0, well, we have this, right? And basically that's the conclusion of the problem. So we're done, right? So basically, in other words, we have proved that. So in other words, we proved that. What did we prove? We proved that for all epsilon positive, right, there exists a delta which is positive such that the absolute value of f of y over y is less than epsilon, provided that y is positive but less than delta. Okay. But by definition, this means that f of x is little o of x. And we're done. All right, so that was the problem. Well, it was a bit tricky. So that was, because you can see, problem A5 in 1954, long time ago though. And now let me do something else. So that was problem number 5, I think. Now problem 6, which it's kind of a converse of the fact that, you know, when we have a continuous function, well, we have seen a theorem that any continuous function will take any compact interval and will transform it into a compact interval. But what if we have some kind of a converse of this? So the problem that I have in mind is the following. So let me have a function, a real value, then define on our function f. So let f be a function which transforms, and this function has the following property. So which transforms any open and bounded interval into an open and bounded interval and any closed and bounded interval into a closed and bounded interval. Well, guess what? The function is continuous. So show that f is continuous. So that is the problem, right? So it takes any open and bounded interval into an open and bounded interval, and any closed and bounded interval into a closed and bounded interval. So then in fact, the function is continuous. Well. So let's see. Well, if one way to show that it is continuous, if we have this right idea, is to show that well, we will show that f has intermediate value property and f is 1-to-1. In the virtue of theorem, I don't remember which one, but we know that intermediate value property plus injectivity will imply that continuity for the function, right? We said this. Okay. All right, so let's show this first. We take care of intermediate value property. We take care of this guy. So let's just show that f has the intermediate value property. And now what we're going to do is the following. So we'll consider let a be. Let me take these two real numbers, and let's just assume that a is less than b, and f of a is not f of b, right? They're different. And consider any lambda between f of a and f of b. So if we show that there exists a c which depends on lambda, let's just call it c lambda in AB, such that f of c lambda is equals lambda, then there you go. We have showed that f has the intermediate value property. So let's show this. And now let's exploit our conditions. Now we know that since this guy, let me denote it like this. We know that f of the closed interval AB, so we said that this is an interval, but not just that, is an interval. This is an interval this is an interval that so how should we say it? So so this is an interval. Okay, that contains f of a and f of b, right? Okay, so so it follows that lambda is in I, right? So there exists, let's say, a C lambda in AB in a enclosed, sorry, not open, but we need to take care of AB such that f of C lambda is the same as lambda, right? Okay. Which but also this lambda, since f of A cannot be lambda, so and f of B is different than lambda, it follows that this C lambda is in this open interval AB. And thus f has the intermediate value property. Finally. Okay, so we're done with this part. Now let's look at the one-to-one. So now assume that, let's assume by contradiction that f is not one-to-one. So in other words, assume that there exists, let's say, AB with A less than B, with f of A equals f of B. And now we'll get the contradiction immediately because we're going to look again. So we know that f of the closed interval AB, we know that this is a closed and bounded interval, but this can be written also as f of the open interval AB united with these elements f of A and B. But this will be nothing else. So we know that this is f of the open interval AB united with f of A and f of B. Okay, but this guy here, f of the interval AB will be some interval. Let's just say alpha open interval alpha beta, and reunited with some elements k, let's say. But this is not a closed interval, interval, which is not a closed interval. Contradiction. So f is one-to-one. All right, that's great. Now we have showed two things. So putting both of them together, so we have showed that f has the intermediate value property, and f is one-to-one. Then we're done. So finally, f has intermediate value property and is one-to-one. So this will imply f is continuous. And we're done. That's the end of the problem. All right. Now let me veer towards something else. I have a couple of more problems to do, maybe 2 or 3 problems, and then I'll stop. But these are very important problems because you'll see some sort of techniques how to deal with them. Anyway, the first problem, so problem 7, from the remaining 3 problems, was a Putnam H3 in 2012. It's a very beautiful problem. Pretty standard, I would say, if you ask me. It says the following. So let f define on a closed and bound on a closed interval at -1, 1 be a continuous function such that we have the following conditions. So the first one was f of x is 2 minus x squared over 2 of f of x squared over 2 minus x squared. So that was the first one. The second one was f of 0 equals 1. And the third one is there exists the limit as x approaches 1 from the left of f of x over the square root of 1 minus x. And we're asked to show that, prove that f is unique and express f in a closed form. So this is how the problem was stated in the contest. In other words, just find that. All right, so let's look at the problem. As you can see, we have a, so f is continuous. That is the condition that we have. But you just look at it here. And we have this functional equation here. You see these two parts. So this will define what we call a functional equation. Well, it's not as a Cauchy functional equation, but it's kind of a functional equation. So we'll have to do something about it. Maybe there is a way to maneuver this. Well, let's see. Well, usually when you have this kind of problems, like I said, they're pretty standard because usually you use continuity. You have to write it in a certain form where you can simplify it a bit. And then you take a sequence, and then you'll see the convergence of that sequence, and then you just play around. Then you use continuity because you know how to take the limit as n approaches infinity, and using the definition of the continuity with sequences, then you can find the function. So let's get going. So let's see. So let's look at the first two conditions. Look at them here. And now, in fact, you can guess the function that verifies this, and we will say that we show that f of x, which is the square root of 1 minus x squared, for all x in -1. So we'll show that this is the function that verifies our conditions. Well, let's see, does it verify? Well, clearly f of 0 is 1. That's easy to see. And the first one, if you look at it, and also there exists the third one is easily verified, right? But the first one, again, is easily verified. Wow. So now, since I put my hands on the function, so maybe there is a way for me to play with it a bit. So now let me consider the function g of x is f of x over the square root of 1 minus x squared. And we'll define this g on the open interval -1, 1, and this will be a real value function. Okay, so now we have this function, g. And now let's see, we like to plug in into the I, so plug plugging in into the first condition, we get that, let's see, what do we get? So we get that, okay, so we get that g of x is So f of x, g of x. Perfect. So is g of x squared minus 2 minus x squared over 2 minus x squared for all x in the open interval -1, 1. All right, so we have this. That's great now. So what we're going to do is now we fix an x in -1, 1, and we define a sequence an n greater or equal than 1 by a1 equals x and an plus 1 equals an squared over 2 minus an squared. Right? We define the sequence an in this way, and now it follows quite clearly that by an easy induction, so by an easy it follows that that an is bounded between -1 and 1. Right, that's very easy to see. And clearly, another thing that's easy to see, okay, is that a sub n plus 1 is less or equal than a sub n squared for all n greater or equal than 1. Yes. And thus, an it will be decreasing. All right, that's great. Now, by the monotone convergence theorem, by MCT, right, it follows that an converges. It follows that an converges to, well, converges to what? If we pass to the limit, so it will be to 0. Or anyway, this is exercise for you. And also, an in absolute value is less or equal than x to the power n. Now, now it's quite clear what will happen since g of an is g of x for all n, and g is continuous. It follows that what? Continuous at the point 0. This is important. At 0. It follows that what? It follows that so it follows that if you pass to the limit as n approaches infinity, we get that g, so the limit as n approaches infinity of an, so g of x will be g of 0. But g of 0 is nothing else than 1 for all x in -1, 1. And also, and for x is plus minus 1 by continuity. Okay, that's great, beautiful. Let's go back and see who g was. Look at it here. G, look at it. So g of x is 1. So therefore, so finally, f of x is nothing else than just the square root of 1 minus x squared. And we're done. Surprisingly, we haven't used the third condition, so it's superfluous. So this guy here has nothing to do with the problem, superfluous. Anyway, so that's surprising. All right, now I think I would like to do one more problem, and maybe, yeah, maybe two, we'll see. So now I'd like to do problem number 8. Which again, it's a Putnam problem. It was a Putnam A3 in 2013. And the problem, it's pretty standard, I would say. So suppose that that the real numbers let's say A0, A1, AN, and X with X between 0 and 1 satisfy that A0 over 1 minus X plus A1 over 1 minus X squared plus AN over 1 minus X to the power n plus 1 is 0. Well, the problem asks us to show that there is, let's say, on y between 0 and 1, such that this polynomial, let's say a0 plus a1 to the power y plus so on an to the power y to the power n is 0. So this is the problem. Okay. Now, let's see. So let's suppose by contradiction that P of y is not 0, right? For y between 0 and 1. Okay, that's good. But we know that this is a continuous function, so any continuous function will have the intermediate value property. So by the intermediate value property, P will has the same sign right, for all y between 0 and 1. And now without loss of generality, let's assume that P of y is greater than 0 for y between 0 and 1. Okay, so we know this. But on the other hand, if we explore this condition here, look at it. This guy here says what? But on the other hand, what do we have? So we have that 0. And if you notice here, this is just the geometric series. And we're going to write it in this way. So this is the sum from k equals 0 to infinity of, so we have p of, so it will be p of x to the power k, right? Times x to the k. All right, so we have this series here. And it's clear that x to the k is between 0 and 1. Well, now we have to analyze this a bit. So let's look at this guy here. So what can we deduce from here? Well, since we know that this guy is between 0 and 1, well, the coefficients, so we can infer that. That's the coefficients. P of x to the power k, right? So these are the coefficients here, these guys. So the coefficients cannot all have constant sign unless we have the following two situations. The first one, let's see what well, at some point it will be 0. So there exists, let's say, a k such that p of x k is 0, which is nonsense, false. And the second condition is that 0 is between two of them. So there exists a, let's say, a k and an l such that p of x to the k is less than 0 and less than p of x to the power l. But again, now it's by the IVT, by the intermediate value property, there exists, let's say, a y between 0, 1 such that p of y will be 0. Again, false. It's a contradiction. All right, so the contradiction will, so where did the contradiction come from? From our assumption that p of y is not 0. So the conclusion follows. And that's it. That's the end of the problem. It's a pretty beautiful but very easy one. Basically, it's just to, the main idea is just to interpret this condition with, write it in terms of polynomials and the geometric series, and then use the intermediate value property. All right, I want to draw your attention with one more problem, and then I'll stop. It's quite long, but I want to do this because it's problem 9. Again, this was a Putnam problem. If I look at it, it was a difficult one, I would say. Putnam B4 in 2000, so 20 years ago. And the problem says the following. It's a very beautiful problem. So let f of x be a continuous function such that f satisfies this condition. F of 2x minus 1 squared minus 2x squared minus 1, sorry, is 2x f of x for all x. Show that f of x is 0 for all x between -1 and 1. Okay, so that's the statement of the problem. Well, as you can see, we have a functional equation, but maybe we can write it in a certain way. It doesn't look like a Cauchy functional equation, though. This is why I'm saying it's a bit tricky. Let's see. Let's look at this condition. It's kind of weird one, but maybe it will ring a bell. If you know some trigonometric identities, maybe it will ring a bell. Because you see 2x squared minus 1 comes from a trigonometric identity. What was that trigonometric identity? Remember, cosine of 2x was cosine squared of x minus sine squared of x, or if you want cosine, or you can write this that well, since sine squared of x plus cosine squared of x is 1, then you can say that 2 cosines with the cosine of 2x is 2 cosine squared of x minus 1. So maybe it will ring a bell to that. You see, you also have there 2x f of x, so maybe it's something involving cosine of x. But first, let's see something. I want to look at some value. And we look at the following value. Let's look at this guy, f of -1/2. And you'll see why I'm looking at this. I'm going to write it in the following way. Pay attention. So this would be f of 2 times -1/2 squared minus 1. Right? Because -1/2 is 1/2 minus 1. And now I'm going to use the condition in the problem, which is, so it will be 2 times -1/2 times f of -1/2. Wow. So f of -1/2 is 0. But maybe -1/2 there is comes from some kind of a value of cosine. Maybe it will be what? Maybe that's f of cosine of 2 pi over 3, right? Maybe that will be 0. Okay. Now, like I said, this rings a bell to a trigonometric identity. So let's do this now. How should I say it? For all x real, we have that f of cosine of 2x is, we know that cosine of 2x is 2 cosine squared of x minus 1. Okay, that's great. And now using the property given, this would be nothing else than just 2 cosine of x, f of cosine of x. All right, that's great. Now, let's see. We have the following implication. If cosine squared of x is not 0, right? It follows that f of cosine of 2x is 0 if and only if f of cosine of x is 0. We have this implication, right? It's quite clear. But this will imply the other, provided that. All right, that's great. But if f of f of cosine of 2x is 0 is equivalent with f of cosine of f of wait. F of cosine of x is 0. Is equivalent with f of cosine of x plus 2 pi is 0, right? And since f of cosine of 2 pi over 3 is 0, now by an easy induction, it follows by an easy induction, and I'll leave this to you as an exercise, that f of, and I'm going to be careful here, cosine of 2 pi over 3 plus 2k pi, everything over 2 to the power n, right, is 0 for all k and n in Z. So you can prove this as I'll leave it to you as an exercise. But now the set, one can prove that, but the set A, and let's denote the set in the following way. So this is 2 pi over 3 plus 2k pi over 2 to the n with k and n integers. This guy is dense in the interval -1, 1. And what do we know? We know that if a continuous function has a value on a dense set, then it will have for all values. Since f is continuous, it follows that f of x is 0 for all x in -1, 1. And we're done. Yeah, it was very, very tricky problem. You'll have, well, in the recitation, I'll do a similar problem to this one. Okay, I think this sums up everything that we have done for this lecture. And you'll see more problems similar to this one in the recitation. All right, guys, thank you very much. I think it's a good place for me to stop right now.